Good morning, students. Today we will continue the second lecture on bonding element complexes 2. I have explained in the first lecture that electronic configuration, what is electronic configuration, I have defined it, and following it the influencing factors which are destabilizing the electronic configuration, that are perturbations, and in this perturbation we have come across internal perturbation, and we also has external perturbation and I also defined it terms, states and microstates. What is term, what is state, what is microstate? I have given the definition, and I have also given the calculation for number of microstates for an electronic configuration. How many number of microstates is, we have calculation part, and following of these topics today we are going to have LS coupling and vector projection for LS coupling, and we also have JJ coupling. Right. Before starting the new topics, I just brief the last last topics. The first one, I have defined it, electronic configuration. In definition of electronic configuration, an electronic arrangement using all four quantum numbers thus principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number, and obeyed all three basic principles that are Aubaou and Hund's rule and Pauli exclusion rule will be called as electronic configuration. Right. The definition will be like this: an electronic arrangement which uses all 4 quantum numbers of principal, azimuthal, magnetic and spin, and obeys all 3 fundamental rules of Aubaou, Hund and Pauli exclusion. Thus the electronic arrangement will be called as electronic configuration. And I have explained what is Aubaou rule, what is Hund's rule, what is Pauli exclusion rule, and also I have defined all 4 quantum numbers: principal quantum number, azimuthal, magnetic and spin quantum numbers. So getting this electronic configuration, the electronic configuration is destabilized by some certain forces. There are some certain forces existing in an atom, in a metal atom, and thus forces which are destabilizes the electronic arrangement will be said to be perturbations, and thus perturbations are existing in an atom, innerly atom they are existing, which will be said as internal perturbation. And there is external perturbation. We can apply some force to destabilize the electronic arrangement, and all thus will be called as perturbations. Thus perturbations are two: internal and external. When it comes with an internal perturbations are two, in which the first one is interelectronic repulsions. Where interelectron repulsion is nothing but, in an atom the electrons get repulses, right? So why it happening, why interelectron repulsions exist in an atom? Once we see, we have to come to know that how minute the atom size and how lesser electron distance covers. If we go that, in generally we will going to hold, or we can see only the materials, right? So the materials only we can see, right? Where the materials are made up of multiple molecules, right? And those molecules which are made the materials are formed by the number of atoms, right? So the materials we will see the larger material, macro things we can see, whereas those macro things are made up of within micro things, right? The micro things here are atoms, right? Atoms are making molecules, and molecules makes the materials, right? So where the atoms will be very small size, right? So here why I am saying this all is, we have to recognize the how smaller the atoms, right? In this atom, when we look into the atom is consisting centrally situated nuclei, were surrounded by multiple energy levels which consist of different number of electrons. Is this centrally situated nuclei, there are energy levels and which are consisting multiple number of electrons, right? Where the electron distance, this atom size only very smaller, right? When we see the radii of atom, it will be counted in terms of Armstrongs, right? Armstrong's units we can count, right? So thus angstrom units size of atoms consisting primary particles such as electrons, neutrons and protons, many more, right? Where electrons, thus electrons consist electrons where the electrons accommodation will have very much closer interaction. The distance covering by one electron to other electron will be very small. The distance will be very short. So far what happens, they get in interaction, right? When the particles getting closer and closer, they will have some certain interaction, right? So here also there's closer packing of atom, the closer packing of electron in an atom will get some interaction between one electron to other electron. So where the electrons what we are having in an atom, they all negatively charged particles, where when there are negative charged particles gets in interaction, thus surely will be repulsions, surely will be count as repulsion. We know that positive particles, negative particles, same charged particle, when they comes closer together, they will have repulsive interaction. And when there are different charged particles, right, opposite charged particle, when they are getting closer one to other, they will have attraction. Where here the negative electrons are getting closer and closer, so far they will have repulsive interaction. This repulsive interaction will destabilizes the atom. Not only this, even when we see the orbital, one of orbital, the orbital can accommodate maximum number of electrons are 2 in an atom. 2 atoms can be accommodated, right? When the 2 electrons are accommodated in an atom, they will be have very closer in one to other, right? One electron and other electron will be accommodated in one orbital, right? They will be have closer interaction, very much closer interaction. When that is happen, again there will be negative repulsions arises, and all this electronic interaction and this electronic interaction will be have repulsive interaction, will destabilizes the electronic configuration. So thus when it is destabilizes the electronic configuration, thus electronic configuration has to overcome the inter-electron repulsion perturbation. So to overcome such inter-electron repulsion perturbation, the atoms will go for splitting of electronic configuration, will undergo in splitting, right? So with the splitting, right, there will be new energy states will be generates, right? So here electronic configuration when get influenced by the inter-electronic repulsion, they will be get splitting. They gets in splitting, generates new energy levels, and these newly generated energy levels will be called as terms, right? Such how the terms will be arises in atoms, right? So when it comes to the definition of terms definition, when it comes, the newly generated energy levels, from electronic configuration due to inter-electronic repulsions, right? So the newly generated energy levels which are from the electronic configuration due to inter-electron repulsions will be called as terms, right? That's how the definition will comes for the terms. So this is the one internal perturbation which is existing in an atom and destabilizing the electronic configuration. Coming to the next perturbation, second perturbation will be said as spin orbital coupling. Spin orbital coupling, right? And this is also internal perturbation only, which is existing in the atom, right? So when it comes the inter-electron spin orbital coupling, this is due to the electron motion. We has charged particle electron in atom, electrons in atom. That has two motions, two types of motions it has, right? Motions that are orbital motion and spin motion. It has orbital motion, spin motion, right? Looking to the atomic structure, it has centrally situated nuclei surrounded by multiple energy levels, where they will consist multiple number of electrons, and thus electron, right, can revolve around the nuclei on the orbital pathway, and also it can have spinning with its own axis around it himself, right? Around it himself it can spin, right? So when it is revolving around the nuclei, it has orbital motion. With this orbital motion, it generates orbital angular momentum. Generates orbital angular momentum, right? And same to that, when the electron spinning its own axis, itself, right? Itself, when it is spinning, it will have spin motion. It has spin motion. With the spin motion, it generates spin angular momentum, right? And thus generated spin angular momentum and orbital angular momentum, right, will couples together in atoms and in atom. So thus coupled spin angular momentum, orbital angular momentum will generate an angular momentum. Totally counts as angular momentum, and this angular momentum will negatively affect on electronic arrangement, right? In previous we has terms, no, right? Electronic configuration with the effect of inter-electron repulsion, it generates new energy states which are called as terms, and those terms which will be going to influence it by the angular momentum, which is nothing but spin angular momentum and orbital angular momentum couples together, and thus generated orbital angular momentum will negatively affects on terms and destabilizes the term. Destabilizes the terms. Destabilizes them, and thus destabilized term has to overcome the spin orbital coupling in perturbation. So far it can be, the atom can be exist in a stable state. So to exist atomic state in stable, the spin orbital coupling perturbation also has to overcome. To overcome the orbital angular spin orbital coupling perturbation, the terms which are destabilized will be get in splitting, right? So with the effect of spin orbital coupling, right, where they generates new energy levels. So thus newly generated energy levels will called as states. it called as states. So when it comes to the definition of states, the newly generated energy levels from the electronic arrangement of terms due to the spin orbital coupling known as states, right? Newly generated energy levels from the terms due to spin orbital coupling called as states, right? Those are the definition we can give for the states. So these are the inter-electron repulsions and spin orbital coupling will exist in the atom, right, which so far it called as internal perturbations, right? So at the stage of states, we can also externally apply some force to destabilize the state electronic arrangement, and thus can destabilize and thus can furtherly split into hyperfine energy levels, and thus will be called as microstates, right? Coming to the external perturbation, where we can apply external perturbation that we can apply is magnetic field, or we can also apply electric field. When we apply such magnetic or electric field in atom, the newly generated states will get destabilizes, right? So to get overcome such external perturbation to exist the atomic state, the states will get in splitting, where it will be have new energy levels, right? So the states will, under influence of magnetic field or electric field, get further splits into a new hyperfine energy levels of microstates, right? So such how the internal external perturbations influences on electronic arrangements and gets new energy levels, thus called various names with an term, states and microstates, right? So now here I defined the microstates definition for the microstates. An allowed combination of ML/MS values for an electronic configuration called as microstates, right? So in an electronic configuration, if we arrange electrons with an allowed combination of ML/MS values, thus allowed combination of ML/MS values will be known as microstates, right? For example, if we go with P1 configuration, right? number of microstates for an p-n electronic configuration. If you go right, p orbital will have 3 suborbitals. We know that, isn't it? So p orbital will have 3 suborbitals such as px, py and pz. Px, py, pz, where this particular single electron in p1 electronic configuration can have the arrangement into an clockwise spin in px orbital, or it can also accommodate in an py orbital in a clockwise spin. It can also accommodate in pz orbital in clockwise, right? These three arrangement can be possible, and also possible of anti-clockwise electronic configuration in px orbital, anti-clockwise arrangement in py orbital, anti-clockwise arrangement in pz orbital, right? So the p1 electron can have all these possible arrangements, right? When thus have all thus possible arrangement, when you look into the ML/MS values, right? Before that, if we have the ML/MS values for px, py, pz, if you thought that px is n plus 1, py may be considered as 0, pz considered as -1. In there, right, the ML/MS values for px electron configuration, it has +1 of ml value plus half of ms value. And when it comes to same when the electronic configuration of py1, then the electron will have ml/ms values of 0 and plus half, right? And clockwise arrangement of pz electron arrangement, pz1 electron arrangement, it has ml/ms values of -1 and plus half, right? Similar to that, all for these three electronic arrangement, the ml/ms values will be like this: +1 minus half, 0 minus half, -1 minus half. And all these 6 arrangement, it may possible for an p1 electronic configuration, right? So as per the definition of microstates, it is nothing but allowed combination of ml/ms values is nothing but microstate, right? For an p1 electronic configuration, we has these 6 arrangements of electronic configuration. For this, we have allowed combination of ml/ms values. 6 allowed combination of ml/ms values we have. So here the ml/ms of +1 plus half is an 1 microstate. So similar to that, this is another arrangement, another allowed arrangement for the ml/ms value. So far it is second microstate, this is third, this is fourth, this is fifth, and this is sixth. So far for an p1 electronic configuration, the allowed combination of ml/ms values are 6, and thus all 6 will be called as microstates, right? So that's how the definition of microstates is there, and that's how the p1 electronic configuration has 6 number of microstates, right? So in last class, I also given the explanation for the calculation of number of microstates for an electronic configuration, right? So that when we see calculation for number of microstates, here we had 3 formulas to calculate the number of microstates for an electronic configuration. We have 3 formulas, right? 3 basic formulas we have, in which The first one is for an electronic configuration p to the power l to the power of p, right? Singly orbital electronic configuration when is there. For that electronic configuration, the number of microstates calculated using the formula of 4l plus 2 factorial divided by p factorial in multiple with 4l plus 2 minus p factorial, right? So the number of microstates for an singly orbital electronic configuration such as l to the power of p, it equal to 4l plus 2 factorial divided by multiple product of p factorial into 4l plus 2 minus p factorial, where factorial is nothing but multiple product of 1 into 2 into 3 into till does number. When it come to an example, for example of p factorial is nothing but it is a multiple product of 1 into 2 into 3 into till p number, right? Multiple product of 1 into 2 into 3 into till p number, right? Like that the factor means, right? So this is the one formula, right? Here we can go with one example of p2 electronic configuration, and p2 electronic configuration we have already discussed, so I will go with an p3 electronic configuration. Number of microstates for the p3 electronic configuration, where here before going for this we have to know that what is L, what is P. L is nothing but the azimuthal quantum number for electronic configuration, azimuthal quantum number, where P is nothing but number of electrons, right? So here when we compare the p3 electronic configuration with L to the power of p, right? This is p3 electronic configuration having only single orbital. So far we are comparing with L to the power of p, where L value of p3 electronic configuration, atomic quantum number value of p3 electronic configuration is 1, and the number of electrons in p3 electronic configuration is 3, that nothing but p is equal to 3, right? So now the number of microstates for p3 electronic configuration is 4l plus 2 factorial divided with p factorial into 4l plus 2 minus p factorial, where when we substitute L value and P value in this formula, 4 into 1 plus 2 factorial in numerator, in denominator, divided by P nothing but 3 factorial, where 4L nothing but 1 plus 2 minus 3 factorial. And here when we summarizing this, 4 into 1 is 4 plus 2 is nothing but 6 factorial divided by 3 factorial, and in multiple 4 into 1 plus 2 altogether 6 minus 3 nothing but 3 factorial, right? So writing the 6 factorial nothing but 1 into 2 into 3 into 4 into 5 into 6, right? That is how we defined at the factorial. Where it come to the 3 factorial nothing but 1 into 2 into 3, right? So again 3 factorial nothing but 1 into 2 into 3, right? Where numerator having 2, denominator having 2, numerator having 3, denominator having 3 will get in cancel, and 2 into 3 is 6, so these two will get cancelled with 6, right? So 2 into 3 is 6, and numerator also having 6, so they will get in cancel. In finally we has left 4 into 5, right? So which get total number of 20, right? So like that we will have 20 number of microstates for the p3 electronic configuration. It's nothing but 20 number of allowed ML-MS combinations are possible for p3 electronic configuration, right? So that's how the first formula. Coming to the second formula, to calculate the number of microstates is for the electronic configuration of L1 L I to the power of P Lj to the power of Q configuration, electronic configuration. For this, where the P equal to Q equal to 1, right? 2 orbital doubly orbital electronic configuration having single electron in each, right? So for that, the number of microstates will have the formula of 2Li plus 1 in multiple with 2Si plus 1 in multiple with 2Lj plus 1 in multiple with 2Sj plus 1, right? So where Li nothing but Li and Lj are nothing but azimuthal quantum numbers for the orbitals, and Si and Sj nothing but the spin quantum number values, spin quantum numbers of the electron, right? Or spin values for the electrons, right? So that is how. So going with an example already discussed in the first lecture. Here also continuing with that, P1 D1 electronic configuration, where number of microstates is equal to 2Li, where it comes to the Li, Lj values we will write, right? Li value of P1 electronic configuration is 1. The azimuthal quantum number for the d orbital is 2, so Lj is equal to 2. Si value for the P1 electronic configuration is plus half. Similar to that, Sj value for second is also half, right? So coming to thus substituting all this in the formula, 2 into 1 plus 1 in multiple with 2 into half plus 1 in multiple 2 into 2 plus 1 in multiple 2 into half plus 1, right? That's come. So here 2 will get cancelled, 2 get cancelled, where we have 2 into 1 will be 2, 2 plus 1 is 3, so 3 into this 2 when cancel, it will be have resulting 1 plus 1, it is equal to 2. So in multiple of that, 2 into 2 is 4, 4 plus 1 is 5, so 5 in multiple of that, 2 when get cancelled, it results of 1 plus 1 will be 2, right? So 3 into 2 is 6, 5 into 2 is 10, totally 6 into 10 is 16. So for a P1 D1 electronic configuration, the number of microstates are 60. Now coming to third formula. So third formula is for the electronic configuration of P to Li to the power of P, Lj to the power of Q, where P near B equal to 1, greater than 1, Q is greater than 1. Electronic configuration for 2 orbital electronic configuration where consisting more than one electron, the number of microstates is equal to 4Li plus 2 factorial divided by P factorial in multiple with 4Li plus 2 minus P factorial in whole multiplication 4Lj plus 2 factorial divided by q factorial in multiple with 4lj plus 2 minus q factorial. So this is what the formula. Coming to an example here we can take that P2D2 electronic configuration. When we compare P2D2 electronic configuration with Li to the power of P, Lj to the power of Q, Li value will be equal to 1 with respect to P2 electronic configuration. P2 P orbital azimuthal point number is 1 and Lj value will be 2 with respect to D2 electronic configuration. D azimuthal point number is 2 and P number of electrons on p orbital, that is 2. Number of electrons q is nothing but number of electrons on d orbital, that is q. So now the number of microstates for P2D2 electron configuration is, where we have to substitute these all Li, Lj, Pq values in the first formula, third formula of microstates, that equal to 4 into Li1 plus 2 factorial divided by P factorial nothing but 2 factorial in multiple with 4 into 1 plus 2 minus 2 factorial in whole multiplication with 4 Lj value is 2, 4 into 2 plus 2 factorial divided with Q factorial, it is nothing but 2 factorial in multiple with 4 into Lj into nothing but 2, 4 into 2 plus 2 minus 2 factorial, which equal to 4 into 1 is 4 plus 2 nothing but 6 factorial divided with 2 factorial in multiple with 4 into 1 plus 2 minus 2 nothing but 4 factorial in whole multiplication with 4 into 2 is 8, 8 plus 2 is 10, 10 factorial divided with 2 factorial in multiple with 4 into 2 is 8, 8 plus 2 is 10, 10 minus 2 is 8, so 8 factorial, where it is equal to 6 factorial divided by 4 factorial nothing but 1 into 2 into 3 into 4 into 5 into 6 divided with 1 into 2 into 3 into 4. So 1 to 4 in denominator, 1 to 4 in numerator will get cancelled. So results of 5 into 6 divided with 2 factorial is nothing but 1 into 2. Right. So similar to that, 10 factorial is nothing but 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8 into 9 into 10. Where dividing 8 factorial nothing but 1 into 2 into 3 into 4 into 5 into 6 into 7 into 8. So numerator having 1 into till 8, denominator having 1 into till 8. So they will get cancelled. Results in numerator 9 into 10 divided with denominator will get cos 8 factor and will have 1 into 2 factor only. So 2 ones are 6, 3 are 2 ones are 10, 5 are. So left 5 into 3 into 9 into 5, where 15 into 45, which results of 675 microstates. So like this, number of microstates for different types of electronic configuration we can calculate by using all three formulas, right? So after all getting this all, you students can calculate the number of microstates for different configurations such as P1, P2, P3 are already I given explanation. So you can go with P4, P5, P6 electron configuration. You calculate for these all four P configuration electronic microstates, and you also calculate the number of microstates for the D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. For all these configurations, you calculate number of microstates by using the above formulas and give your answers as comments in the YouTube or you can give your answers to my WhatsApp number.